nth root of x minus beta k from 0 to n minus 1, where zeta n is primitive nth root of unity. And this is what equal to what? Sorry. This is equal to beta minus alpha, right? And again, we see that principal divisors supported on the poles of x. And if we take all of them but one, we obtain independent divisors. It's easy to verify. If n equal to 2 and alpha, beta, gamma, simple roots, then take square root of x minus alpha, square root of x minus beta, and square root of x minus gamma, and then it's not enough to take just square root of x minus alpha minus square root of x minus beta, and square root of x minus alpha plus square root of x minus beta, and they will be dependent. But what we can take principal divisors square root of x minus alpha minus square root of x minus beta, and square root of x minus alpha minus square root of x minus gamma. And again, independent principal divisors. Well, there are some other examples which are less interesting, so these are most interesting examples. Well, I don't know a single case, again, of effective Ziggy's theorem in this absolute sense that I stated, which does not follow from the theorem and the covering argument. There is, well, of course, I would be happy to find new examples when it applies. And there is one question which is pretty it's an interesting question, but I do not know how to answer, and which is related to this statement. As I said, the very condition of whether there are, so the very condition B is decidable. You can verify it using just reducing it to some question about lattices. What is, however, not decidable is whether you can find an étale covering of the initial curve where this condition is satisfied. This I don't know. And so the following, it is, so the following question can be of some interest in the context of all these problems. Let X be a curve over Q bar and P a point Is the following question decidable? So the following decidable. So there exists a morphism et al. Outside P, outside our point. Ramified everywhere, but can be ramified at P, such that there exists a principal, a non-trivial, non-zero principal divisor on X tilde, supported above so we have here a point, here we have some points above, and we want to make a principal divisor of them. Since there are many morphisms like this, for each concrete morphism we can decide whether it is true. But whether such a morphism exists, we don't know. Each non-trivial example of such a morphism would probably lead to a non-trivial example of effective Ziegler theorem. But decide whether it is in principle, whether one can give an algorithm just starting from X and P and no other data, to whether such guy exists or not, it's an open problem. I don't know. I asked to many mathematicians, some very renowned mathematicians, and well, so far the only response I got some 20 years ago that it is some new example that I did not know, and people showed me some new example. And this is all. So on the curve of genus 2, if we have a curve of genus 2, then besides the obvious cases when the poles of X contain an orbit of an involution, there are some other cases where a thing like this is true, and then we have effective Ziegler theorem. But in general, I don't know. So it's an interesting open problem. Of course, generically, if we just take over C, generically it never exists. But I don't know what happens over Q bar, because generically means that the set where it exists is a union of countably many of, if we take on some modular spaces of objects like this, of cuples X of punctured curves, then this condition simply means that we have countably many guys where it is true, and of smaller dimension. Of course, I cannot cover all the modular space over C. But if we reduce to curves over Q bar, then a priori countably many guys can cover it. So there is even little hope. I do not totally discard the possibility that it is always possible when it is over Q bar. Something like Bell's-like statement here. I'm pessimistic, but I'm not 100% pessimistic. Because Bell's theorem in the beginning also looks like some strange statement, but it's true. Okay, and last interesting application of this is modular curves. So I will now make a very, very brief tutorial on modular curves, which basically, so if you don't know at all modular curves, then it will hardly help, but I believe that everybody in the audience more or less saw what modular curve is. So it will be rather to just to fix the language that I use rather than to introduce. So let me start from a brief tutorial on modular curves. So brief revision of modular curves. So let H be the Poincare upper half plane, so all numbers of. We can also view H as sort of space of lattices. So if lambda is a lattice on C, then lambda is isomorphic to a certain lattice tau 1, where tau is in H. So we always can every lattice as isomorphic to a lattice of this kind, of course. But it is not the full, so the correct set of representatives of isomorphic lattices, because two lattices of this kind themselves can be isomorphic. And we say, and it's easy to see that two lattices, tau 1 is isomorphic to tau prime 1, if and only if there exists a gamma that tau and tau prime are related by a unimodular integral matrix. So there exists a gamma in S to Z such that tau prime is tau gamma, where we usual sense of gamma is A, B, C, D, and then tau gamma is A tau plus B over C tau plus D. And so we consider the space of isomorphism classes of lattices is just H. So we denote SL to Z, we denote it as a group gamma of 1. And now, this is what I said, that this gamma have nothing to do with the multiplicative groups gamma that I used in the previous hour. And it is denoted by Y of 1 is the classifies lattices up to isomorphism. But since every lattice, what is lattice? Lattice it is a dual object to elliptic curve. So to every lattice we associate elliptic curve. And two elliptic curves are C-isomorphic if and only if the corresponding lattice is isomorphic. So it also classifies elliptic curves. So complex elliptic curves. Elliptic curves up to C isomorphism. up to C isomorphism. And since to every elliptic curve we associate its J invariant, and we know that two elliptic curves are isomorphic if and only if when they have the same J invariant, so we have that J invariant. J invariant is a give the bijection between y of 1 and C is bijection. Now, y of 1 is a quotient, so now let's consider it as analytically it is a Riemann surface. And it is not a compact Riemann surface, it has one hole in it. It is, and we can compactify it. How we compactify? We add one point, which is called the cusp. And it is done as follows. So consider extended Poincare plane. So extended Poincare plane H bar is H, and we also add the point at infinity and all rational points on the real line, so P1 of Q. And then, if, again, our group gamma of 1 acts on this, because here it acts and simply it's just one orbit, and this orbit exactly gives the missing point that we have to add. So there is some work to be done. One should show that some topology can be correctly introduced. It's all written in books like Shimura or Lengo, whatever. It's subtle. It's not this compactification. Compactification is never totally obvious. It's some subtle job, but it is, say, for instance, in Shimura's book, which is otherwise not very readable, but exactly this is well done there. So one can read it. And so, by gamma of 1 is called x of 1, and it is y of 1, and one more point, which is the image of this, which is called cusp. And this is already a compact Riemann surface. And J is rational function on it. It's a rational function on this compact Riemann surface, having the pole exactly at the cusp. It's a simple pole. And I believe that it has 0 at I, right? Which corresponds to the most wonderful, which elliptic curve, x squared plus x. So I always forget, or x squared plus 1, I always forget. Or x cubed plus x, or x cubed plus 1, I always forget. But it corresponds, I is 0. No, I think it is when the x coefficient is 0. So, yes, x cube. You need I to be roots. Yeah, okay, I always forget it, yes. So, anyway, yes, it's simple pole, which means that since it has only one pole and it's simple, it must generate the whole field. So, actually, C of x of y, x of 1 is just C of j. So J generates the field. So sometimes x of 1 is called just J line or whatever. I prefer to separate it, so not to call it J line, I prefer to consider J as just x of 1 is some object having sort of structure of moduli space. So it classifies elliptic curves together with one degenerate elliptic curve, which correspond to the cusp. And J is just an isomorphism of this guy with the usual P1, which does not bear any structure of modular space. This is what my point of view, sort of esoteric point of view. Of course, this gives isomorphism, so we can identify the two, but I prefer to view it like this. And the cusp goes to here to infinity. Now, x of 1 as it is, so it is curve of genus 0, so as is, it is not a very interesting, guy. So more interesting are modular curves of higher level. So instead of gamma of 1, we consider gamma of n. Gamma of n is consists of matrices which are congruent to the unit matrix mod n. Where n is positive integer. And again, if we have h by gamma of n is called y of n. And so this gives clearly that since gamma of n is subgroup of gamma of 1, this defines natural map from y of n of y of 1, which means that every point here is elliptic curves with something in addition. So to every point here, we have many points here. What is in addition? And y of n actually classifies elliptic curves with additional n-level structures. So y of n classifies triples E, P1, P2, up to a C isomorphism, where P1, P2, some bases of n torsion. So n torsion we know is free abelian group generated by Z by NZ squared. So we have some basis of this guy. Again, we may compactify, but now there will be not one cusp, there will be many cusps here, which correspond to, here there can be many kinds of degenerations. I don't go into this topic, take Silverman and everything is written there. I think it's more second volume of Silverman rather than first volume. So x of n is just the extended by gamma of n. And this is called the principal modular curve, so it is equal to y of n. And cusps, many cusps, but finally many cusps. And again, we have j as a rational function here. And now, this is compact Riemann surface. And as such, it is again an algebraic curve, and j is a rational function of this algebraic curve. But now the poles of j are all the cusps. So there are many poles, so j does not generate this field, and in fact it cannot, because it's usually a field of already starting from n equal to 2, it's field of chi genus. So it is not genus 0. And so it is curve. It is algebraic curve of certain higher genus, and it is called principal modular curve of level n. And gamma of n principal modular subgroup of level n. So now, so far we defined this over C, so using it as a transcendental definition. So it's like elliptic curve modulo lattice, it's transcendental definition. But it turns out that it has a natural model, which is defined over a number field, and not just over a number field, but over the cyclotomic field, Q of zeta n. Defined over Q of zeta n. And if we consider the field Q of zeta n, so the field of rational functions, and we take it over Q of j, now notice that this covering, or well, corresponding x of n to x of 1 is Galois covering. So the corresponding function field is Galois extension, because this is a normal subgroup. It is kernel of the isomorphism, right? So this is normal subgroup, because gamma of n is a normal subgroup of gamma of 1. And this again is a Galois extension. And the Galois group is, in certain sense, is almost naturally, well, I say almost because one should choose some basis and then it becomes naturally isomorphic to Galois group is isomorphic to GL2 of Z by NZ just by plus minus 1. Which means, and here what also if we look carefully, that we will see that, so why is plus minus 1? Well, let us look carefully. Here, if we have this, consider the tower of the field, Q of zeta n of x of n, now it has Q of zeta n of j and Q of j. So here is the geometric part, the same field. So here, if we replace this by C, for instance, will be same Galois group. And here, the Galois group is SL2. And why it is by plus minus 1? Because we want this Galois group to be gamma of n, gamma of 1 quotiented by gamma of n, which is SLN to Z. But the point is that plus minus 1 and gamma of 1 acts trivially. So minus 1 acts trivially. So we have to quotient by this. And here it is the this group quotiented by this group. So it is simply what? It is the determinant who acts. So here is Z over NZ, which is exactly the Galois group of the cycloatomic field over Q. So the determinant, if we take here a matrix, then the determinant of this matrix corresponds to the action on the constants. And the matrix and the part which is of determinant 1 is exactly the geometric Galois action. So it looks like this. Good. Now, if we have a subgroup so for more details on how all it works, I know two sources. An older source is Lang's book, Elliptic Functions, where there is a chapter where he explains in details how this Galois action works. Well, in Lang's style, but it is readable. And there is a newer book of Diamond-Schurman where all this is again explained. But I think that more or less same quality of explanation. Good. Now assume that we have a subgroup G in GL2Z by Z, and which contains plus minus 1. Just so to be specific, I must take a subgroup here in the quotient group, but it's easier to take a subgroup here and assuming that it contains plus minus 1 to simplify the life. Then it gives rise, by Galois theory, to certain subfield of this field, right? Over Q of J. And this gives rise, this will be a certain field of function on certain curve, which we denote by xg. And this curve has a model which comes from this model on the field Q of zeta n, and how the G invariant, the G invariant part of this field. And so the G invariant part is how the determinant of G acts on this field. In particular, if the determinant of G is full, G has matrix of every determinant, then it will be simply over Q. Just let me illustrate this by some example. And xg is called the modular curve of level n, and it classifies xg classifies elliptic curves with a level n G structure, well, whatever it means. So it is just words. It doesn't mean anything, just words. But in some cases, it is in some special cases of G, it is clear what this G structure means. And so let me consider some examples. So most interesting example if we take G as the triangular group, or Borel subgroup. Then Xg, well, maybe I should also say that what is Xg of the set of complex points at Xg is just H quotiented by gamma, where gamma is the pullback of G to SL2, right? That pullback. So not the whole G. We can pull back only the part of G, which is of determinant 1, but we can pull back it to of G to SL2. That's it. Good. In this case, Xg is the most famous modular curve, X0 of n. And gamma will be simply gamma 0 of n. So the matrices in SL2Z, which are 0 mod n in the left lower. So Denis Benoit also speaks on them. So I think that I don't have to speak much on them. And what is the G structure? Simply the G structure means n isogeny, cyclic n isogeny, or cyclic subgroup of order n, right? And classifies couples E A, where A is cyclic n isogeny, E to some other curve E prime. Now, G, the determinant of G, so any determinant can be, the determinant of G is what? Is just everything. Which means that X0 of n has model, so defined over Q. So this becomes Q, simply, right? And so we can speak about, so it is just we defined it totally analytically, but at the end we obtain an algebraic curve over Q. And we can ask what are rational, Q rational points, or more generally, K rational points, where K is any number field. Now, what is X0n of K? It is up to, besides the cusps, let's forget about the cusps, besides the cusps, well, it is cusps. By the way, I did not say much about, it is easy to see that the number of cusps here is equal to the number of divisors, not the number of divisors, some function depending on the divisors. Particularly, there are 2 cusps when n is a prime number, and at least 3 cusps when n is a composite number. So some function depending on the divisors. So anyway, so it's cusps, and so let's take away cusps, or we obtain y0 is what? Are couples E A, where E is elliptic curve over K, and A is an K isogeny cyclic K isogeny of order n. So it classifies elliptic curves defined over K, which have a cyclic n-isogeny also defined over the field K, which is a priori totally very, very strong condition about the curve, why it should have such an isogeny. Or it has a subgroup, a cyclic equivalent condition. It has a cyclic subgroup of order n, which is defined as a subgroup, as a set over K. Not every elements are not, maybe not defined over K, but as a set, it is defined over K. And here, there is, for instance, a wonderful theorem by Barry-Mazur, and very non-trivial, called rational isogenies of prime degree, that for P greater than 163, x0 of P prime number of Q, consists only of the cusps. In other words, there is no elliptic curve over Q can have a Q isogeny of degree, prime degree P exceeding 163. So it is strong and non-trivial theorem. So one more example, and I finish for today, and we continue on Thursday. So on Thursday, I will speak a bit more on modular curve, how Baker method applies. Then I will speak on Runge's method, and show also how it applies to modular curves. Good. So one more example. So we can also consider what is called this is called Borel subgroup. Consider what is called Cartan subgroup. So let us, just to simplify, assume that n is a prime number, which is the most interesting case for, at least for me. N is a prime number. And then GL2 of Fp in this case has two types of maximal semi-simple subgroups, maximal abelian subgroups, which is called split Cartan subgroup and non-split Cartan subgroup. And they are unique up to conjugacy. Has of maximal abelian subgroups. Split Cartan subgroup and non-split Cartan subgroup. So what is split Cartan? Split Cartan is just diagonal subgroup or a subgroup which is conjugate to it. Non-split Cartan, it is more difficult to describe, but it is, if instead of Fp you take reals, then it is just rotations and homodities. So it is like this. And the Cartan subgroup, whether it is split or it is non-split, is not a maximal subgroup. And moreover, it has a non-trivial normalizer. say over R, if we, instead of FP, we take R, then we know that we take rotations very well, but if we, it is index to subgroup in the group generated by all symmetries and rotations. So if we add any symmetry, then we obtain a bigger group, right? And the split Cartan, again, we have what is in R. It is just, how it is called, well, expansions in one direction or the other direction. But if, again, if we add the symmetries, we obtain something bigger, and this will be order, yes. And this will be index 2 subgroup. So each of them, so each Cartan subgroup has a non-trivial normalizer in GL2 of FP, in which it is a index 2 subgroup. And the interesting guys are modular curves corresponding to these normalizers. So we have the following modular curves. X SP of P is corresponding to split Cartan subgroup. X SP plus of P corresponding to the normalizer of split Cartan subgroup. X NS of P corresponding to non-split Cartan subgroup, and X NS plus of P corresponding to the normalizer of non-split Cartan subgroup. And again, one can speak about, again, all these are defined over Q. And one can speak about rational points. Well, I think that I have finished now. I will continue on Thursday at this point. And one can speak about rational points. At least in this case, there is some natural description what it means in the language of elliptic curves. And I will also speak about some results that can be obtained in general by Baker's method and also by the other method, Runge's method, that I will introduce on my last lecture on Thursday.